Okay, so we will start. So we discussed last day about uh, different categories of time complexity analysis, starting from the every case, worst case, and best case. So today we will take up the tricky one, that is the average case. So as the name suggests, here you have to estimate the number of times the algorithm does the basic op on average. Now this part is a bit tricky. So what do you mean by doing the basic op on average? So the idea here is to assume some sort of a distribution on the input. Okay, so this will get clear if we take an example and see. So again, let us get back to the sequential search algorithm. Okay, so now uh, suppose X is in the array. Suppose I tell you this, that X is in the array. Okay, so do you have any reason to believe that X would be in the beginning of the array, or the middle of the array, or the end of the array? Is there any reason to believe so? If I just tell you that X is in the array?
No, sir.
No, sir.
No. So that means, what am I trying to convey? I'm trying to
Means its location is not.
yeah, it's not fixed. Probabilistically, what does it mean?
It will be somewhere from.
It is equally likely that
It is
Different
equally
way.
likely. So it is equally likely for X to appear anywhere in the array, right? So therefore, there is no a priori distribution that we are assuming. Okay, so it is equally likely that X could appear anywhere inside the array. But can you think of a situation where a search is happening and you can assume an a priori distribution? Some example, some real life example.
Excuse me, sir.
Yes.
Like if we have an array of newses, like news,
Huh?
and the latest news is mostly searched, so the latest pushed item in the array would be more probable.
Okay. Fine. Um, okay. I would say an okay example. Something more day to day. How do you search uh, for a particular word in a dictionary?
alphabetical order.
Basically,
First letter.
it is
Yeah. So,
always in order.
so there is there a rationale behind assuming an a priori distribution?
Yes, sir. It is sorted.
Yes. So in this case, there is a rationale behind assuming an a priori distribution. However, it is not true in this particular sequential search case. You guys probably have not seen, but when we were young, there used to be telephone directories, and telephone directories were also organized in alphabetical order of the names, and therefore there also this a priori distribution makes sense. Assumption of this a priori distribution makes sense. Okay. So then, if X is equally likely, what is a way to estimate the average case, average time complexity? So what we again need to do, as I already told you, that we should typically try to follow this format. So here the basic op is again comparison. Input size as usual is n. So now the analysis. So as we said that X can be anywhere in S. So we will take we will try to make this estimation in two steps. First, where we assume and in the second one, so this is the number one, number two, X may or may not be in S. So we will make this assumption first and try to estimate the average case time complexity, and then we will try to generalize it. So this is the more general situation. Okay. So let us consider the kth location of the array. Okay. So the probability that X appears in a particular location how much is this?
1 upon n.
1 upon n. It's equally likely. Okay. Fine. So if X is in the kth slot, okay, what is the expected number of basic operations?
K.
K. Expected number, this is probabilistic. Think carefully.
The N.
N.
Yes.
It's in the kth slot.
Sir, one.
Okay.
One, sir.
1. If
K.
X is in the
Oh, it's
kth,
K by N.
yes.
K.
Oh, sir. Okay,
So the expected number, that's why I'm telling it's expected. Expected number of basic ops is K by N, right?
Yes.
Sir, can you
So,
explain why K by?
huh?
Why K by N?
Why not K by N? what is the expected number?
So it should be K only. The
Why?
basic.
Why? First place 1 by n. Second probability expected number that the basic op will be done 1 by n. Second place 1 by n. Third place. So this is all probabilistic
Okay.
because x can appear at any of these positions. So at the kth slot, k by n.
Sir, but shouldn't the number of basic ops be an integer or something like a digit instead of?
This is again, as I said, so this is a probabilistic estimation. Okay, this is a probabilistic estimation. So now if I call an as the, so these are all abstract. These formalisms are all abstract. Okay, so then an, so now x could be on any one of these locations, right? That is, k could be anything. So what is the range of values of k?
1 to 10.
1.
So this is the average case.
Sir, I did not understand K by N. Still.
So according to you, what should be the
Means,
value?
sir, what is means expected number is actually probability, or it is number of operations which we expect?
It is probability. So have you forgotten expectation of a probability?
I am not aware about this definition.
You have to read it. You have to read it up. So
Basically, it's like it is a summation of that PIXI.
absolutely, it's a summation of PIXI.
Okay, sir.
The probability into the number of times that it happens. So you have to brush up your probabilities. I mean, I'm sorry, this is too advanced a course for teaching you the basics of probability. So you have to go back and get your probability and statistics corrected. So I was assuming that in your class 2, expectations and probabilities had been taught in details. And also, I'm not sure, like in your first year, there should be some engineering mathematics where probability was taught, wasn't it?
So the probability course is currently going on. And
Yeah, but in
class
class,
there was no subject only probability.
no, there was no subject, but there was a part, right?
In first year there is no. There was
No. In your class 12, there was nothing.
Yes, sir.
Huh?
We had that. Sir.
Yeah, in your JE, there was no probability.
It was there.
Okay. So these are, yeah. So these are
This definition was very less used. Like I don't remember using it in
no.
J10. So
Yeah.
yes.
So you have to get back. You have to get back. Yeah. So you have to get back and brush up. So it's basically PIXI. Pi is the probability and number of times that event happens. Okay. And the sum of this. This is the average. Or so when you say like average on probabilities, it becomes your expectation. Okay, that is what we are computing here. So then this becomes, so this is something, guys, you have to very carefully understand.
Sir,
Huh?
sir, shouldn't it be K running from 1 to n?
I can't get you.
Sir, in the summation you have written I running from 1 to n.
Sorry. Yeah. Thank you. Yeah. This is K K running from 1 to n. Yeah, thanks for the correction. Yeah, so the average case becomes n plus 1 by 2, okay, when we assume that x is in S. Now we have not solved the full problem. We have to now consider the case and address the case where x is not part of, I mean, x could be or may not be part of S. Okay. So let us say that we assume that x is part of S with some probability P. Okay. So then x is not in S with probability how much?
1 minus
1 minus
1
1
minus P. Okay, very good. So again, now finding x at any location inside S still equally likely, but then what is the new probability?
P by n.
P by n. Okay, now basic ops. If x is at K is
PK by N.
so here the average case is if it is inside the array and if it is outside the array,
N.
N.
only n.
N. Yes.
1 minus p.
1 minus p.
n into 1 minus
Oh,
p
1 minus.
with p inside the array with 1 minus p outside the array, but here you have to go all the n steps. So this finally will give you, if you do some algebra, this will give you n into 1 minus p by 2 plus p by 2. Now, it's always in this kind of proofs, it's always good to check the boundary condition. P is equal to 1. What will be the value?
N plus 1 by 2.
N plus 1 by 2.
N plus 1 by 2. And what does this condition refer to?
Will surely be
X is
So
in the
X
array, sure.
is surely in the array. Surely in the array. And this is what we found out earlier, right?
Yes, sir.
So this was the case where we assumed that X was inside the array. So as I said, this is the general case. Okay. So, and this is the special case where you set p to 1. Now you can have various p's. Now suppose there is half and half chance, okay, that x is present in the array and x is absent in the array. There is half and half chance of each of these. So in this scenario, an is equal to
3n plus 1 by
3n, sorry, 3n by 4 plus 1 by 4. Okay, so that means roughly, if you have an idea that x is like with half probability inside the array and half probability outside the array, roughly the number of times the comparison that needs to be made is 3n by 4. So that is 75% of the array needs to be compared to, probabilistically 75% of the array needs to be compared to ascertain that x is present or not present. Okay, so this is what is like kind of the interpretation. So all of you have come across quicksort?
Sir, I have doubt.
Go ahead.
Sir, in the above expression, yes, sir, this a of n, above. Yes, sir. So in this outside the array one, so why it is n times 1 minus p? Because I think it should not be there in first position and it should not be in their second position, and so it should be like in powers, not
Why?
multi.
Why are these dependent events?
Yes, sir.
Are these dependent events? These are all
So because in an array,
independent of each other.
sir, in array, means what is in the position 1, it is not
So
dependent
you
on.
don't so you don't get at position 1 minus p is the probability. Don't get at position 2, 1 minus p is the probability. Don't get at position 3, 1 minus p is the probability. That's what is summing up into n into 1 minus p.
No, sir, this is and, so I multiply now, sir.
Why?
Sir, because I don't want in first position and I also don't want in second position and I also don't want in third position.
No. Why should it be and?
So because I want the
Each position is independent of the other.
Yes, sir, and I also don't. Okay.
Each position is independent and each position has the probability of 1 minus p. As simple as that.
And sir, one more thing, if it is not present in the array, then the number of comparisons made will be n plus 1.
Yes.
So it should be n plus 1 into 1 minus p.
Okay, that's fine. So that constant we are not anyway considering. वो constant का तो कोई value ही नहीं है finally in comparison to n, because we are assuming that n is large compared to a constant.
Okay.
Okay, so now with this we are all set. Okay, so I was asking something. So how many of you are aware of quicksort? Have this been taught to you in PDS?
Yes.
Quicksort?
Yes.
Okay. So
yes,
this will be anyway again taught by Pawan in the divide and conquer chapter, but just an early warm-up exercise. You will not be able to do average case complexity if you are not brushing up your probability statistics well. So all the average case complexity will be based on the idea of probabilities. Okay, so you will assume some distribution of the inputs, and based on that you will do the computation.
Sir,
Huh?
sir, what is the notation of average case time complexity?
I showed na AN.
Okay, sir.
Okay, so now we will start gearing ourselves up for the notion of order. Okay, so before doing this, we will talk about something called a complexity function. What is a complexity function? Now, a complexity function is a special type of function that maps an integer to a non-negative real. Examples: so these are all examples of complexity function where an integer is mapped to some non-negative real. So
So, uh, so the integer it takes as an input has to be non-integer as well, na?
has to be
Non-negative as well.
of course, a positive integer.
Okay.
Okay, so now complexity functions which look like this these are called linear functions. That is linear in n. Similarly, these are quadratic. Quadratic in n. Now, these again have categories. So if a complexity function or a quadratic complexity function does not have any linear part, then it is called a pure quadratic function. Whereas if it has a linear part, then it is called a complete quadratic function. Okay. Now, one more thing before we go into the exact notion of order. Linear function is always eventually, mark the word eventually better than a quadratic function. So consider two algorithms, okay, A and B. A runs in time 100n. N is the input size. And B runs in time 0.1 n square, or say even lower, 0.01 n square. Okay, so which one do you think is better and why? I mean, in terms of computation of the basic op.
A is better.
Sir, it dependent on size, na sir.
It will depend on n.
It will depend on n. So can you comment on n? When will A be better?
When n is very large.
We will equate this to 100 n equals to 0.01 n square and find n and find inequalities.
10 ki power 4.
N greater than 10 power 4.
Very good, very good. So when will be better than B? So if I ask you this question, your answer will be whenever n is larger than 10 power 4, A starts getting better than B. Now, this is a choice of a design engineer. Now, if the design engineer knows that these two are the time complexities of the two algorithms, and if the design engineer also knows that my input is never ever going to be larger than 10 to the 4, then I'll always use B. However, if it is going larger than, naturally my input size is much larger than 10 to the 4, then I will resort to using A. So that's why we said that eventually, so when n is large, so in the limit of large n, okay. So now, with given all this, we are now ready to introduce ourselves with the notions of order. So sometimes what happens is that it is, can you please mute yourself? So sometimes it often happens that it is difficult to do the exact time complexity analysis as you have seen earlier. For certain algorithms, it is possible, but for many algorithms, it is not possible to exactly identify what is the number of basic ops. In such cases, we try to, estimate something that is close to, or in other words, in the order of, that's where the name order comes in the order of some complexity function. Okay, so the first one among this is defined as follows. For a given complexity function, Fn, big O of f of n is the set of complexity functions for which, say, complexity functions, let's call them Gn. The set of complexity functions Gn for which there exists a real positive constant, say C, and a non-negative integer, say capital N, such that for all n larger than equal to capital N, Gn is less than equal to Cfn. Such complexity functions Gn are said to be in big O of Fn. This notation is called the big O notation, and also the asymptotic upper bound. Asymptotic means eventual. Okay. So pictorially, how will it look? Suppose this is Gn. So what will be the nature of Fn? How will it look? Or Cfn, whatever. Cfn will be above Gn or below Gn?
Above.
Sir, above.
Above. And suppose this is the capital N. So what does the definition mandate? What does the definition mandate?
Cfn should be above Gn for all points to the right of capital N.
Very good. So something like this, right? So as soon as n becomes larger than or equal to capital N, after that, for all values of n, Gn will be upper bounded by Cfn. Okay. Now let us try to find out some upper bounds. Simple ones to start with. How will you show this? Typically, you will have to find out, you will have to reason out for a suitable C, comma capital N.
So C equal to 6, N equal to 0.
You need 6.
Smallest possible integer.
Smallest possible is 6.
Sir, 5. We can take 5 only.
Can I write this?
Yes, sir.
Yes, sir.
It's also possible.
Yes, sir, if we take equal.
So some choice of C, and for n equals 1, I can write now a bit of a tricky one. So extend sort, remember? That we did in the last class. What was Tn?
N minus 1,
22.
N by 2.
How will you do this?
Sir, C equal to 1 by 2. For
C
all
equal
n.
to 1 by 2.
Natural. For all
So
natural
say
numbers.
n for your friends. Say if I assume n greater than 0. So assuming that capital N equals 0, I can write n into n minus 1 by 2 is less than n into n by 2. Can I write this?
Yes, sir.
Yes, sir.
Now,
Sir, will there be any harm if anyone shows instead of half, say 5 or 10?
no harm. Any C is possible. As we said, there exists. So the condition on C is there exists C. So how will you do this one?
The C
This
equals
is
1,
easy.
N equals 1.
Okay, so we have done some examples. Now your task is to go back, find in Google many such exercises where they will give you a complexity function and ask you to show that it is in big O of something, n square, n cube, etc. Try those. Okay, I'll also send you problems once the class is over. I'll also send you some problems, and you also try to find out. There are many problems. Believe me, hundreds of such problems. Okay, and the more you do, the better you are in getting the tricks as to how to do it. The second and an equally important bound is called the asymptotic lower bound. So again, here for a given complexity function, Fn omega of Fn is the set of complexity functions Gn for which there exists a positive real constant C and a non-negative integer n such that for all n greater than equal to n, you have Gn is greater than Cfn. We also say Gn is in omega of Fn or lower bounded by Fn. So how will the function look here? Suppose this is Gn.
So the graph will come down like below of Gn.
My drawing is very bad. Okay, so this is the asymptotic lower bound. Now, same problems. Let's revisit. Can you show this one? This one is not very hard.
So 5n square is greater than like any c times n square and c is less than 5.
Yes.
Sir, here also we can take C equal to, right?
Yes. Yes.
And
It's also
both
possible.
Now,
Sir, can C be 0?
N must be greater than 0, no, sir?
yeah, n must be greater than 0. Yes. So what did we define as C? What was the definition of C?
Sir, real constant.
Positive real constant.
Okay, sir.
All your Grand Viva, as you go up, the BTech Grand Viva, dual degree Grand Viva, everywhere, one of these two questions are very typical. Define big O, define omega. Never forget the clauses.
So here shall n be greater than 0 or greater than 1? Because in the previous case you mentioned it is 1.
Any n that is suitable, as long as this condition is satisfied.
Is there no condition on n, sir? Like
So
n should be any positive.
No, so it's any n. So it has to be a non-negative integer. That's all. But after that value of n, for all cases, this should be satisfied. See the definition.
For the values less than n, is it necessary that it should be less than it?
No, no.
Okay.
So we are silent about what is happening for values below less than capital N. We are only interested in cases where the definition specifically talks about cases where it is larger than equal to n. Why is it this? Can you tell me from the intuitions that we have developed? Why larger than n is important and lesser than n is not?
So large size data will affect more.
So remember, every time we are interested in the asymptotic or the eventual behavior. So therefore, we are only interested in values of small n larger than n. Okay. So only that happens in the asymptotic limits. Extend sort. Can you show Tn is in omega n square?
Yes, sir. So we can say that n square.
Here you cannot do for values less than n. For values less than 2. For values larger than 2, true? Is this true?
Yes.
Yes, sir.
For values larger than 2, you can say this. So now, given these two, the upper bound and the lower bound, the most interesting thing that we are often like in search of is the tight bound. Can you guess what it would be from the name?
Both sigma.
So it is
And both
both upper bounded and lower bounded. So theta, this is denoted as theta. Theta of Fn is O of Fn intersection omega of Fn. Okay. So theta of Fn means the set of complexity functions Gn for which there exists two positive real constants, say C comma D, and some non-negative integer n such that for all n greater than equal to n, Cfn is less than equal to Gn is less than equal to Dfn. So just now we have seen that Tn is in O of n square as well as it is in omega of n square. So this tells us that Tn is tight bounded in n square. Okay. So roughly this is all about orders. So there are a few more notations like a small o of n. So a small o of n is almost similar to big O of n, but with one special constraint. So earlier we said that in big O of n, there would exist a C. Okay. In big O of n, we said that there should exist a C. For small o of n, it should be for all C. Okay. For every positive real constant, the definition should hold the same definition. So basically, what we say is that for a given complexity function, small o of Fn is the set of all complexity functions Gn satisfying the following. For every positive real constant, say C, there exists a non-negative integer say capital N such that for all n greater than equal to n, Gn is less than equal to Cfn. So this C is for all C. This is the difference from the big O where it is for any C. Any one C, if you can find, that is good enough for big O. But for small o, it has to happen for all positive real constants. Okay. So,
Sir,
yes.
Sir, for different values of C, can we choose different values of capital N, or
That
we
is
have
possible.
to?
Yes.
Okay.
Yes, that is possible. Yes. That is possible. Now, can you show this? Just give me an idea. We'll stop here. But tell me, like, how will you do this?
By contradiction?
By contradiction. So, very good. By contradiction. What will you assume? That n is in omega n square. Then what has to happen?
N shall be greater than C of
N
n.
should be greater than Cn square. Okay. And therefore, 1 by C should be greater than n. And what does this contradict with?
C shall be positive real.
So that means for n greater than 1 by C, this cannot hold, right? The inequality does not hold. So that means that in general, for n greater than any capital N, this inequality will not hold. And thus we are in a contradiction. Okay. So just for 1 by C itself, it will not hold. Therefore, for n greater than some capital N, it will not hold. So it is holding in the first part of the curve. But after the curve, you don't know. After that point, you don't know. After 1 by C, you don't know what is happening. Okay? So therefore, in general, it will not hold. And therefore, n is not in omega n square. So this kind of proofs might appear in your exams. So try to practice more and more. Okay. I'll send you quite a few practice problems, but you also try to find yourselves and solve. We'll stop here. Thank you for waiting a little bit more.
So please share the notes.
Yes, I'll share the notes.